Okay, welcome back. So we're going to discuss today reinforced concrete column design using BS8110. Okay, so let's discuss actually loaded column. So for example, we have here given is the size of this beam. Okay, the beam is 600 mm in depth, and then you have your assumption for FCU is already given, and then also for your FY, and then for example you have already computed the load, which is 1100 kilonewton for the dead load, and then also you have for the live load, which you can get it from the table. So for example here, so first you have to check if that is short or slender with these conditions. Okay, so for example this one, basically at the top it's 600. Here at the top, this is 600. This is greater than the size of this column, which is 300. So this is condition 1. Okay, so that's why you have here condition 1. At the bottom, maybe this is not, it's actually not designed, the footing is not designed to resist any moment. There's no like tie beam, so the condition is 3. So from here you can use you have condition 1 at the top, and then condition 3 at the bottom, then you have 0.9. okay, as your beta. You multiply it by 4.5. 4.5 is this one, okay, the clear height. So multiplying it by 4.5 or 4500 will give you this LEY. Let's say EY and LAX are the same, so you can have these values. B and H are the same, so this is 11.6 less than 15, meaning this column is short. In the case if this is greater, for example, you can have here 6, 16 or 17. If this is 17 greater than 15, what do? You just have to increase B or H. Okay, so this is a condition, as I said. If for example this D is greater than, for example, this H, then you have condition 1. Otherwise this is condition 2. If you have the same condition at the bottom, could also be 1. Otherwise you have your 2. And if you have in the ground floor, let's say in the footing, there is some moment resistance in your structure, then it's also condition 1. okay, otherwise it could be condition 3. Okay, so we do this by getting the value of n. What is the value of n? Okay, well, the value of n is just the dead load and then the live load combined using this factor 1.4 and then 1.6. In this case, dead load and live load is given to be just the same. So you have here your value of n. 3,300 or times 10 to the power 3 becomes Newton. This is kilonewton. This is the area of your column, which is, for example, this is 350 and then 350. So this is 350. So this part is the area of the concrete, which is just equal to area of concrete. This one, right? Area of concrete is equal to area of column minus area of steel. That's why you have here this area of steel. And then you have 0.67. You just have to substitute. Okay, 0.67. Okay, and then you have FY 500. Let's say you use 500. So you can compute area of the steel bar. So from here, the requirement is 4938. You go to the table, you just look for the value of 4938. Okay, for example, how many pieces of 4938? Now you can have a combination. Okay, 4 pieces of 32 and 4 pieces of 25. 4 pieces of 32, you have 3220. Okay, and then 4 pieces of 25, you have 4 pieces of 25, 1960. So adding these two will give you 5180, which will satisfy the requirement of 4938. Okay, so this one satisfies the requirement. So you have 4 pieces of 32, this big one, and then this one at the middle is 4 pieces of 25. Now, what's the size of the link or stirrups? According to the code, it should be 1/4 of the maximum size of your main bar. Main bar is maximum is 32, so that is 8 millimeters. Okay, so we can use 8. Okay, the code says it should be not less than 8 millimeters. Okay, so how about the spacing? It should be 12 times the diameter of the smallest bar. So the smallest bar here is 25. So 12 and 25, not 32. Okay, because according to the code, it should be the smallest. Okay, it should be the smallest. You have 12 and 25 will give you 300, and then the other condition is smallest section. Okay, this is a square, 350 and 350, so it doesn't matter. Okay, whichever the side. So you have 350. Between 350 and 300, of course, you use the smallest value, which is 300. So this will be the spacing. So your link or stirrups is 8 mm diameter, spaced at 300. Take note, the smallest main bar, smaller main bar is in between. At the corners are the bigger one. So as simple as that. Okay, so for example, we present you the simple design steps. Okay, so for example, you are carrying, we're talking here about the top. Okay, this is framing plan. Okay, we are speaking about at the top. So the area coverage, this one is 5 meters. Okay, so meaning we take 1/2 of his and then 1/2 of here. So this is 2.5 from the center. This is also 2.5. So it goes to, like, you have 5 meters. Okay, the same here, you also have 2. That is 1/2 of this one, 4/2. Also here, that's 2. 2 and 2 becomes 4. Okay, you have the sizes of this and then this one. Okay, so this is the area that you're going to carry if your column is somewhere here. Okay, if your column is here. So you get the value of the slab, you just get the volume. Okay, unit weight, the volume of the slab is 5 meters by no, this is 4. Okay, 5 meters by 4 meters. Okay, and then you have thickness, which is 0.2, or you may assume, depending on your thickness. So we have 120 kilonewtons, the weight of your slab. And for your beam, you have for this 5 meters, this one, you have 0.25 by 0.6, 5 meters. This is the volume multiplied by the unit weight. And then for this one, you also have 24, and then the length of this one is 4 meter. The section is 0.25 and 0.5. Of course, you need also to add the unit weight of the column, like the self weight. Okay, so you have 24. The height of your column, for example, this one, okay, like that. Okay, if you're going to take the isometric, so this size is let us say your assumption is 0.3 by 0.3. The height is like, clear height is like 3.5 meters. Okay, so you get the volume, section, this is the area of the section, and then the height multiplied by the unit weight. We have this weight of the column. Okay, so we can add the total dead load, 120, 30, and 7.56. You get the total load, and the live load is 4 kilonewton per square meter. That's the assumption that we have. Just multiply it by the area of the slab. Okay, take note, only area. So you have this one. Using this combination, 1.4 dead load, then you have 1.6 live load. We get this combined load, axial load, acting on the slab. We try also to check if the condition of this one is short or slender. Okay? Again, the same approach with what we have. That condition 1, if you have this state or this condition. Okay, we can, if this one is the same as above, so this is 1 and this is also 1. So in this case, this is 0.75. So meaning it's less than 15, and that means this is short column. Now it's greater than 15, as I said, you can just increase edge or section so that it would satisfy the condition on short column. Now once you have this one, you can use this sizing of column to check if your assumption is correct. So let's say we consider 3%, or you can use between 0.4% to maximum of 6% according to the code. So as to compute this area of the column. Okay, so we can calculate this one mathematically using your calculator. So this case, this is just equal to 15,000 square millimeter. The area is h times h, meaning you can calculate h. This is less than our assumption, so we can have our assumption as maybe, of course, we increase 200 or maybe 200 by 250. It's up to you. Okay. Now, from here, just take note again that the reinforcement that we are going to consider, okay, that we have to check. Okay, we use this one 0.4 to 6%, and then we design now the steel bar. Okay, using this formula. Okay, using this formula, you have 0.4 FCU 0.75. Okay, so we use 0.4 FCU, area of our assumption 300 by 300, area of the reinforcement that the one that we are going to calculate. Here mathematically we say A is negative because our load N is quite small, okay, because we are just like calculating a small value, a small load that is being carried. So this one could be reasonable, okay, but if you're going to carry, let us say, times 2 or times 3, you have how many floors? Column, ground floor, you have like this, okay, many here, maybe footing, ground floors, first floor, second floor, third floor. You can have times 2 or times 3 to check, okay, if what would be your AS. This one's negative, meaning it doesn't require much that of steel bar. Even if we're going to decrease the size, let us say 250 by 250, or we decrease FY, okay, it's still negative. So in this case, if you have like this kind of a result, then we check with the minimum value. Our minimum value is 0.4%, divided by 100, that becomes 0.004. This is the area of your column. This will be the value. Now if you are going to increase it into 1%, so this could be the requirement. Okay, going back to the table, we need 625, and this one could satisfy. Now take note that you better choose even number, like 4 pieces, 6 pieces, or 8. Okay, so here we use 16 mm, so that's why you have 16 mm. No, here you have 16 mm 4 pieces. Now for the size of your link, according to the code, it should be 1/4 of the main bar. That's 4 mm. That's smaller than what is required in the code. So we use, according to the code, the smaller value, which is 8 millimeters. Now the spacing, it's 12 times the size of the main bar. The size of our main bar is 16, so that this will give us 192. And then the size of the column, 250 and 250. We use 250, it's the same because they are square. And this, for example, you have here another one is 200. If there's 200, so we could use here 200, okay, but in this case this is 250. Between 250 and 192, of course, we decide to have the smallest one. According to the code, it should be the smaller value to give us much safer value for the link. That's why you have 8 mm diameter with a spacing of 190 millimeters. So that's all. Designing actually loaded column is much like very short, okay, so much easier. So next time I'm going to explain to you the design of column subjected to flexure. So that's all. Thank you.